So, we are going to start the lecture number 25, which will be an extension of the last lecture 24, and this will be on magnetic properties of nanomaterials. As you know, we have discussed about electrical properties, thermal properties. Magnetic properties are very important for nanomaterial, because many of these materials are actually in applications due to very outstanding properties they show or exhibit. So, in the last lecture, we have discussed about mostly magnetic properties of materials, not in details of magnetic properties of nanomaterials. And today we are going to talk about some aspects of the effect of size on the magnetic properties. But before that, let me just have some recap. I will always try to say this question to you, that please, when watching a lecture video on your computer or mobile or tab, do write your questions. It is not possible that you will understand everything in this lecture. So, better write it down, and whenever I am going to discuss with you these lectures, then it is easy for you to ask questions. Otherwise, you have to formulate the questions at the time. So, please keep in mind that these lectures are very specific. So, this will not be complete in sense of starting from magnetic material and then talking about what is the effect of size. So, we are actually having limited number of lectures for each of these topics. So, we have to be very careful about what we are speaking. So, as such, magnetic materials are basically affected by the magnetic field, right. So, magnetic field can be produced simply by passing current through a coil, we know that. And if you pass current through the coil, it produces a magnetic field. Now, if I keep a material inside the magnetic field, this will lead to induction of magnetic effects. Okay. So, that means there will be change in terms of magnetic moments from the electrons. That is what happens. So, depending on that, as such, all the materials in the world can be divided into several categories of magnetic materials. Like you can have diamagnetic materials which oppose the magnetic moments. In fact, this all the material in the world inherently show some diamagnetic properties. So, therefore, origin of diamagnetism is basically found in the orbital motion of electrons of the atoms acting like a tiny electrical current loops, and that can produce the magnetic fields. So, in an external magnetic field, the current loops will align in a way to oppose the applied magnetic field. So, therefore, dielectric materials are exposed to a force pushing them out of the magnetic field. That is why they oppose the magnetic moment. Okay. These are not important for our discussions, but for the sake of completeness, we need to talk about it. Then the next category of material is paramagnetic materials. They are significantly stronger than a diamagnetic, and it produces magnetization in the direction of the applied field. So, in a paramagnetic material, the atoms can act as a tiny magnets or dipoles basically, that may be oriented by an external magnetic field. So, situation for paramagnetic material in absence of external magnetic field is what I have discussed in the earlier lecture. Important materials are basically ferro and ferrimagnetic materials, and they show large magnetic induction effects. And ferromagnetic materials basically they have unpaired electron spins of the atoms, and that can interact with each other, and this can lead to long range phenomenon called the lining up of the dipoles in the material, and therefore, they show pretty strong magnetic moments. So, depending on that, you can have hard or soft magnets. Hard magnets will have a high coercivity, soft magnets will have small coercivity. And then we have also discussed about in the last lecture about the storage magnetic storage media, like the magnetite or thin films of cobalt, platinum, chromium, or cobalt, chromium, tantalum, just which is used in the glassy on a hard drive actually. So, that is something which is very important. So, in a nutshell, this slide shows you everything. All the material in the world shows diamagnetic behavior, and but some of them show paramagnetic behavior, which is much stronger. the important for us for this consider is the ferromagnetic or ferrimagnetic or antiferromagnetic materials. Ferromagnetism can be of these three different types. In case of ferromagnetism, as I already told, the unpaired electrons or what is called the unpaired electron spins of an atom can align by application of the magnetic field, and they can then interact, and if they align equal strength of magnetic spins aligned, then you call it ferromagnetic. And sometimes it may happen that you can have equal and opposite spins aligned, and so therefore net magnetism is 0, but the material has spins available. You can also have a situation in which you have uneven values of the spins, opposite spins. That is what is shown in case of ferrimagnetism, and so therefore this leads to a certain kind of a finite magnetic moments. So most important things are basically ferromagnetic, which shows a strong magnetic coupling effects. Okay. So that is what will be our discussion in case of nanomaterials. So these are the electronic spins are shown here. In the parametric materials you see here, a distribution of the magnetic moments are randomly or arbitrarily, but in the ferromagnetic material they are actually coupled and they aligned in the parallel with respect to the magnetic field. Okay. And in case of antiferromagnetism, they are having, as we just discussed, you have a spins which are parallel but opposite, so they cancel out. And in case of ferrimagnetic material, the values of the spins, okay, magnetic moments of the two parallel sublattices do not match. So there is a resultant magnetic moment present, and it can be useful for various applications. So there are three types of this ferromagnetic material. Nanomaterial material I have not shown because their moments will be very weak and completely random. So this is again same picture shown in a broader sense, so that you can see very clearly how the molecular magnetic moments exist in a paramagnetic and ferromagnetic materials. Well, this is something which I have shown you. So this can be quantized in terms of magnetic susceptibility. What is that thing can be quantized? The magnetic induction. The moment you pass current through a coil, it produces a magnetic field. Then if I put a material inside this, the magnetic field effect will be felt in terms of induction. So that can be quantized in using a quantity called magnetic susceptibility or chi. So normally chi can be three types: 0, more than 1, or more than 0, or less than 0. So chi actually measures the material response related to the vacuum. For the vacuum, value of chi is 0. So for greater than 0, that means the magnetic induction is very strong, like in ferromagnetic or ferrimagnetic materials. Less than 0, like in paramagnetic materials, the effect will be very weak, not seen much. So therefore we can actually calculate, or we can actually write an equation of induction in terms of applied field and the permeability. So that is equal to 1 plus chi multiplied by mu 0 and h. Mu 0 is the permeability of the vacuum, that is nothing but 1.26 to the minus 6 henries per meter. So if you plot the magnetic induction versus magnetic field, B versus H, then you have value of chi which is very large and more than 0 for ferromagnetic material like magnetite, nickel ferrite, or ferrimagnetic material like ferrite, cobalt, nickel, gadolinium, and value can be as high as 10 to the power 6. Then you can also have situations where the chi is 0, there is nothing effect on that. If chi is 0, then B is equal to mu 0 h. Okay. Whatever will be applied magnetic field, that will multiply to the permeability of the vacuum, and then induction is very small, because permeability vacuum is already minus 6, right. So you need to apply a huge magnetic field to induce certain kind of a magnetization or magnetic induction in the material. So aluminum, chromium, moly, sodium, titanium, zirconium, and a vacuum, all of them show chi equal to 0, there is not much induction possible in this material. And lastly, for diametric materials, the chi is negative and very small. So therefore, even if you apply huge magnetic field, nothing is going to happen, because spins are cannot be aligned. So this is very easily available. You can read from book of Callister. So in terms of magnetic moments, diamagnetic materials, you see, when you don't have no magnetic field, there is no effect. And when you apply magnetic field, there is opposing effects. Okay, opposing effects of the magnetic field comes. That's why the the most of these materials which show diamagnetic behavior, they oppose the magnetic lines of forces. And the best example is the magnets which shows such a kind of behavior, where this is the magnetic lines of forces and the spins are aligned opposite to these lines of forces. So, therefore, they cancel out. Okay. For paramagnetic, without any magnetic fields, there is some random arrangements. So, net magnetic moment is 0, but the moment you apply magnetic field, there is some arrangement possible, okay, for the spins or the magnetization moments, and these will align, but not properly with respect to the field. So, therefore, effect will not be strong. For the ferromagnetic material, applied magnetic field will make sure that these spins are aligned to the field directions, so that the magnetization effect is strong. Okay. Not only that, there is a long range effect on the alignment of the spins also. What I mean to say by that is that if you apply magnetic field, the spins will interact with themselves. There is exchange coupling happens between the spins, and they will allow them to align in a particular directions and then strengthen the induction effects. That is something which is very common. So, that is all. So, therefore, if I want to look at a detailed manner the ferro and ferromagnetic materials effect of magnetic field. So, this is something which is all of you have studied, and nothing need to be told again and again. Then instead of saying that if I apply magnetic field and slowly the magnetic induction increases and then it reaches a maximum value where it saturates. So, that is something which is mainly because of the alignments of the domains in the materials. Okay. Domains are what? Domains are actually magnetic regions where the magnetic spins are aligned in a particular directions. So, in a material with a multi-gun structure, you can have domains aligned in different directions. So, as you apply the magnetic field, so this field strength will make the magnetic domains to be aligned along the direction of the field. Okay. And finally, when all the magnetic moments are aligned to the direction of the field, the magnetization gets or magnetic interaction gets saturated. So, there is no further increase of magnetic induction possible. So, then if you reverse the magnetic field or reduce the magnetic field rather, or decrease the magnetic field. So, what will happen is that at a certain value of magnetic field, okay, there will be some amount of, when you have zero magnetic field, that means when you remove the magnetic field completely, still there will be some amount of magnetic induction or magnetization will remain in the material. So, that means magnetic memory will be not only completely lost. Okay. So, that is what is known as a remnant magnetism or remnants. Now, if you keep on doing the same thing, again you go to negative directions like this way, okay, each become negative. So, you need to have a certain value of negative magnetic field to make the magnetization 0, okay, B 0. So, B is 0 at certain value of AC. So, that is what is known as a coercivity. So, negative H needed to demagnetize. Okay. So, you understand, first thing you are doing is you are magnetizing by applying a magnetic field to the ferromagnetic or paramagnetic material. So, this way a magnetic moment aligns with the H, okay, or the applied magnetic field. So, in a multi-grain materials, the magnetic moments will be aligned in different directions. So, the field strength makes sure that these magnetic moments align only in the direction of the field. So, then you have a high magnetization, but when all the magnetic moments align in the direction of the field, no further increase of magnetic induction is possible. So, then magnetic induction reaches a saturation point, followed by if I decrease this magnetic field. So, I could see for a when I remove the magnetic field completely, still the magnetic moments or magnetization does not go to 0. There is a remnant magnetism remains in the material like a memory effect, and that is what is called as remnants. Then you can further do that, keep on going down in the negative directions. So, you will reach a value of AC for which the B will become 0. So, there is a negative H required to demagnetize the material. Demagnetization means you apply the magnetic field in such a way that all the spins align in opposite directions to the magnetic field. So, then there is no magnetic induction. Well, so therefore, there are two important parameters you learn. One is the remnants, other one is the coercivity. These two you should remember. So, for a soft magnetic materials or hard magnetic materials, important aspect of this loop which is getting complete. Okay. So, if you magnetize and demagnetize, you are going to have a hysteresis loop, right. So, I am not going to discuss, this is taught in class 2 or maybe the first year of physics. So, if you magnetize and demagnetize, you are going to have a hysteresis loop, because the paths will not follow the same. So, therefore, there will be a magnetic loop or the hysteresis loop created. So, this loop will be different for a soft and hard magnetic material. For a soft magnetic material, this loop will be thin and small. For the hard magnetic material, loop will be thick and big. So, what does the loop tells you? Loop tells you the product, okay, B into H, that is nothing but magnetic energy. So, in a hard magnetic material, the product will be very high, that is what you need. If you want to use a permanent magnet, you need to have a very high value of B and H multiplication. For a soft magnetic material like for switching operations, you need to have a very small value of B into H, B multiplied by H. Okay. So, for small coercivity is good for electric motors, you understand that, right? Because you are switching on and switching off. So, every time you are switching on and switching off, if the area is large, you are losing a lot of energy. So, this energy will come in terms of heat. So, that you do not want. You do not want motor to be heated, right? You want motor to run or rotate. So, this is the things you should know very well. So, this is shown in this picture taken from Dieter chapter number 8. As you can see here, that this is the remnant magnetism here or here. So, when field is 0, some kind of a magnetic induction remains in the material, that is what is called remnants. Coercivity is the negative field required to demagnetize, and saturated magnetization is the highest possible magnetization which can be reached upon application of magnetic field. Okay. So, remember these terms and how they look like. Well, so now the question is important in a ferromagnetic material. Why such a kind of things happens like this one? Okay. Why such a kind of things when field is 0? How these domains actually align? So, in a ferromagnetic materials, you should to understand that magnetic energy, because magnetic reasons. Okay. By the way, in ferromagnetic materials, what is known as a dipole or these spin dipoles, they can be represented by unpaired electrons or rather unpaired electron spins of an atom. They interact. They actually, that is why they have a long range alignment of the spins possible, and this leads to a long range ordering of the phenomenon, which can cause line up of the dipoles parallel to the magnetic field, right. So, but for energetic reasons, you cannot have in a bulk material all the spin align to the field, right, directions, because that will be energetically very costly. Okay. You have many other things in the material like gain boundaries, you can have solid atoms, you can have impurities. So, those will forcing everybody all the spins align in the direction of the field in a material is very expensive and costly. So, therefore, size range where this parallel orientation occurs in ferromagnetic material is always limited. Okay. That has to be limited, otherwise it will lead to it will be very energetically costly, and these ranges are actually known as the magnetic domains. That means each of these areas you see here, you can see each of these is a one domain. So, you create a domain separate from the other domain by a wall, and these walls are called as a domain walls. As you see here, this is domain wall here. Okay. There is a domain wall, there is another domain wall here. So, these domains are separated by walls or domain walls. Okay. So, situation is something like that. Now, I do not know whether I have a picture. Yes, this is what is shown here. You can see in a big grain like that, there are alignment of the spins parallel the different directions. Okay. And they are separated by these dotted lines. These are called walls, okay, domain walls, and these walls are called block walls, because this was first described by Bloch. Okay, a scientist name called Bloch. Now, the question is very simple here. So, if I have a domain 1, if I have a domain 2, the spins in the domain 1 and domain 2 are opposite, you can see. So, when you want to the changeover of spin happens through this block wall a very systematic way. That is what I was telling. So, if you want all the spins to be aligned properly, and then it is energetically very costly. So, this alignment of these magnetic moments can happen across this block wall through a reorientation of the spin. So, it was like this, then slowly the spins reorient to the block wall, and at this on the other domain 2, this is domain 1, suppose this is domain 1, this is domain 2, and domain 2 they are aligned in opposite directions. and therefore these walls are called block walls. So that means each of these domains are separate from other one by a block wall. So block wall has certain amount of energy. You must be asking me this question, sir, why not align all of them in one go? Well, that will be very costly, because then you have to have a very long range effect across the whole sample, and that requires the field to be very high or extremely high, which is impossible to achieve even. And not only that, because of the magnetic anisotropic effect, crystalline anisotropic effect, it is not possible. Each grain has a different crystallographic orientations. So that is also not possible, because magnetic spins will always like to align in the direction which is easy magnetization directions. Like if you think of pure iron, and you think of three important directions of pure iron, okay, and one is the 1 0 0 directions, other one is 1 1 0 directions, other one is 1 1 1 directions, okay, the three important directions, right. Now, do you think the magnetization effect, or the all of them are same on all the directions will have same effect? Answer is no. In fact, 1 0 is easy base magnetization direction compared to the other two directions. That means if a grain is oriented along 1 0 directions, it is easy to magnetize by applying field. Then it is oriented along 1 1 0 or 1 1 1. That is something which is very well known. So this is a qualitative sketch of magnetic domains in a polycrystalline materials which can happen. And these dashed lines which are shown here, they are actually demarcation between different magnetic domains. The dark curves are basically gain boundaries. So in a polycrystalline material, this is what will happen. You have gain boundaries, and within the grains you will have different domain walls present. So now this is something which is available in the books of Donald Askeland and others, Science and Engineering of Materials. You can also see it internet available. So these block walls, actually in reality thickness of each block wall is about 100 lattice constant or even more, and block walls may connect magnetic domains with orientation difference of 90 or 180 degrees, and size of the domain and the width of the block walls are always determined by the thermodynamical aspects, which I am not discussing here. So direction of magnetization within the grain is changed by moving the block walls. You can change them, you can move the block walls, then you can actually, that means what? You can actually change, if you apply magnetic field, you can change this block wall positions, then you can change this direction of magnetization. So if you move this block wall, all these pins will align parallel to this domain 1. That is what happens in a real material. So as you keep on increasing the strength of the magnetic field, that is what is shown here, what is happening? Each of these pins are slowly orienting along the field by moving the block walls, okay, by movement of the block walls. So that is something which is perceived to be happening in materials. Am I clear? So it is important to note that existence of magnetic domains and block walls make it easier to change the direction of magnetization. That is why this concept is useful. And so most magnetic materials, the specimen will remain magnetized to some extent after the removal of magnetic field. And this is what is I already discussed about remnants. And this tendency of material to remove the magnetic field, magnetic history is what is known as hysteresis loop, correct. So therefore, let me see whether I have a picture, okay, no. So therefore, upon knowing all these aspects, now we can move what is the effect of these things on the nanomaterials. Okay. So what do you think will happen? So therefore, the effect of size will be mostly on coercivity and the remnants, and also on saturation magnetizations, right. There will be some additional effects also which we will discuss much later, but as you understand, the effect will be mostly on remnants and the coercivity. So how does it happen? So domains walls represent a region of high energy, right, as the spin vectors are not in the direction of the easy magnetization. Hence thicker wall represent higher energy, and material with high magnetic crystalline anisotropy, okay, has the domain walls very thin. Okay. What is the meaning of magnetic crystalline anisotropy? That is what I discussed already. Okay. So every material, crystalline material has different directions of orientations, right. If you consider pure iron, it has 3 important directions of orientations. So magnetization effect on each of these directions are not same. So therefore, the crystalline orientations dictates the magnetic induction. If I apply magnetic field on a single crystal of iron which is oriented along 1 0 0 directions, and another single crystal which is oriented along 1 1 0 directions, and third one along 1 1 1 directions. the one which is along 1, 0 direction will magnetize fast and easily. Okay. But on the other hand, one which is oriented along 1, 1, 1 directions will be most difficult to magnetize, although pure iron at room temperature is ferromagnetic, right. So, this effect of crystalline directions is what is known as a crystalline anisotropy. That means, if different direction has different values of magnetizations, okay, energy required. So, that has cost, that is what is known as a magnetocrystalline anisotropic energy. And in case of rare earth material, this is pretty high, their hexagonal crystal structure, in fact, this is much higher, therefore, domain walls are thinner. So, as you know, domain walls actually has sufficient energy. Okay, so, if thicker domain walls means more energy, thinner domain walls means higher lower energy, right. So, in order to keep the domain wall energy smaller, for rare earth materials, the thin domain walls are created, because otherwise, because of high magnetic crystalline anisotropy energy, it will be very high. Other source of anisotropy will be shape of the particles. Okay, that is something which is understandable, shape of the nanoparticle, shape of the any material, grains actually, and also decidual stresses. Okay. So, competition between this magnetic crystalline energy, magnetic energy and the magnetic crystalline anisotropic energy essentially basically decides the domain size and side. What is magnetostatic energy? The energy which is making the spin align. Okay. So, what essentially is used here, because like magnetic elastic energy due to magnetic restrictions, everything also contribute to the Borel energy, but magnetic restriction is only possible for certain category of materials. So, hence important aspect for you to know is the total energy of the system can be treated as a exchange energy, anisotropic energy, magnetoelastic energy and the external energy. External energy means the total magnetic moment in the external magnetic field. That means, when you apply magnetic field, what is the external energy? In the book of Michael Ashby things, they have written the same equation in terms of like this: E total is equal to E exchange plus E anisotropic plus E demagnetization plus E applied, that is external. Okay. So, what is exchange? Exchange energy is what? Exchange energy is the if energy is related to basically, and this is equal to written as m dot h. Okay. M is the magnetization vector and h is the external applied magnetic field. So, if you apply magnetic field, okay, then you can get effect on the material in terms of energy like this way. Please remember that. Now, the tendency of magnetization vectors to align in one direction is what is gives the exchange energy, and that is quantum mechanical. Okay. Because this tells you interaction between atomic magnetic moments, and this is what is lead to tendency for the magnetization vectors to align along the field directions. Okay. That is something which is very important. If the magnetic moment is very high, very large, the resulting magnetic field can drive the nearest neighbors to align in the same directions. You got it? So, you have many magnetic spins there in the material. So, if magnetic energy or magnetic moment is very high or sufficiently large, the magnetic field can then drive the nearest neighbors to align in the directions. And this is only possible when exchange energy is much higher than the thermal energy, because thermal energy, which is in terms of kT, can always lead to destabilization of the spins. Okay. But only when the exchange energy is much higher than the thermal energy, if you have applied the magnetic field, then only you can align the spins in the particular direction to the field, correct. Second term, which is nothing but anisotropic energy, is basically tendency to align parallel to specific crystallographic axis. That is what I told you. So, 1 0 0 1 1 0 or 1 1 1 in pure iron, and they are all called easy or difficult axis of magnetizations. So, therefore, submagnetic materials will exhibit low anisotropic energy, hence hard magnetic material will use so high anisotropic energy. That is obvious. Submagnetic materials can be demagnetized, magnetized very easily. That is why they have a very small pH loop, right. But hard magnetic material is not easy to do that. That is something which is very important. So, therefore, both exchange energy and anisotropic energy will try to order the spins to align parallel to the magnetic field, right. But in case of third one, which is nothing but a demagnetic magnetization energy, okay, is related to the magnetic field dipole character or spin, and this can lead to, this is what leads to magnetic domains actually. Just now we discussed few minutes ago. Thus, for a microscopic magnetic material, all the magnetic moments are aligned in the magnetic directions, although magnetism vectors of different domains are not parallel. All the magnetic spins will align in the direction of the field, but magnetism vectors of the different domains will not be parallel to each other. Each domain is magnetized to saturation with the moments and typically align the easy directions. So, depending on the ratio of the anisotropic demagnetization energy, this can be open or closed structures. Okay. So, that means depending on this energy, the domain walls can be open or closed. And the last one is the applied energy, which is nothing but a Zeeman energy. This is also known as a Zeeman energy. Zeeman means the same Zeeman we discovered many things. Zeeman energy. Okay. Zeeman has 1 n, not 2 n. Am I clear? 1 n. So, however, so therefore, this is something which is you need to know, and there is the effect of these on these aspects. So, let us now discuss what is the effect of size on this material. So, important aspect of defect of size in material is this cohesivity or remnants, as I told you. So, let us talk about effect of size as a function of cohesivity or remnants. So, you can see here it is grain size. Let us suppose start with, this is something like 100 nanometers, this is 10 nanometers, 1 nanometer, this is 1000 nanometers, and this is 10,000 nanometers. Okay. So, for a bulk material where grain size is more than 100 nanometers, okay, so something like let us start from 10,000, you can see the particle size has no effect on the cohesivity. That is obvious because you have multi-domain particles and particles contains block walls. So, therefore, if you apply magnetic field, slowly the magnetic spins are aligned to the field, and then you can reach a saturation, and then your field required to demagnetize the materials or its cohesivity is also remain constant. But below a certain size, it seems as soon as the single domain particles below a certain size means when the particle size will become smaller, then you can have a single domain particle. That means what? You can do away with this block walls. Okay, particles are small, so that they can have a single walls. Okay, the single walls means the single domain means only one domain. Each particle has a single domain. So, there is no suppose in a big particle you have two domains and domain walls. That will not be there in the single domain particles. In that case, the magnetic cohesivity or remnants will increase very rapidly and reach a very high value, correct. So, therefore, this is something which is very important. So, if you consider the dependency as a function of particle size, so large magnetic particles will be always subdivided by the block walls into the magnetic domains, and the size of the block walls and magnetic domains are controlled energetically. So, therefore, remnants and cohesivity will be largely independent of the size. They will not be effect of any size. That is what you see here. There is no effect of any size. On the other hand, decrease the particle size leads to size ranges when particle will consist only a single domain. There will be no block walls. So, particles become smaller and smaller. So, therefore, one small particle become a single domain particle. So, as the block walls are not there, so therefore, cohesivity and remnants will increase drastically. That is what you see here. Cohesivity and remnants increasing drastically, right. Oh, sorry, I should change my color of these things, so that you can see very easily. So, this is what happens, it increases very rapidly, you can see that. And these particles are mostly employed for magnetic data storage, correct. But if you further decrease the particle, something else happens. So, if you further decrease the particle, remnants and the cohesivity start dropping. That is what you see. This is dropping, further drop, and in fact, it reaches a very small value, 0 almost, when particle size become very small. And these are the range of particles which are called super paramagnetic particles. Okay, paramagnetic we have seen. Okay, this is called super paramagnetic particles. So, this size, critical size where it will happen, will be decided by the time constant. What is written as a tau 1 or tau 2 or time, tau m basically measuring methods. How we are measuring it? Okay. Every method has a time constant, right? Whether we are measuring this VSM, we are measuring using speed, there are different times constant there. So, this changeover will depend on the time constant. So, what is the reason for this phenomenon? Let us first discuss that. Magnetic properties of isolated domain particles or a group of such interacting particles can be observed here like this. Okay. So, supermagnetic particles, within supermagnetic particles, elementary magnetic dipoles are oriented parallel. Okay, you can see here, they are parallel, correct. While the magnetic interaction of the particles is negligible, so orientation of the particles remain random. What is the meaning of that? Within these supermagnetic particles, the magnetic dipoles are parallel to each other, but from one to other particle there is no interaction. So, therefore, the orientations from one particle to other particle become random. Okay. And this happens because of the thermal energy, okay, kT terms. So, that makes this orientation random, and because of that there is no exchange among the particles from one particle to other particles. So, all the spins in different particles do not align in one directions to show a strong magnetic effect, and that is what happens in superparamagnetic material. Okay. So, that is the main reason for this happens. Main reason for this is that materials retain the orientation of their magnetization, but because of magnetic anisotropy. The most dramatic way is observed when the thermal energy of the particle is greater than the anisotropic energy, correct. I am not going back again to anisotropic energy, I have already explained to you. So, therefore, you will have a point in which thermal instability will occur. Thermal instability means thermal energy will misalign the spin of the particles. And however, in case of interacting superparamagnet, like on the right side, interaction superparamagnet, additional phenomena will also observe. So, superparamagnetic particles are of equal size and their distance allows dipole-dipole interaction. That means these dipoles will interact among the particles, and this can lead to a very high magnetic effect or the magnetization actually. So, therefore, you understand the difference between superparamagnetic and superferromagnetic material. Paramagnetic means random, or paramagnetic means they are proper or aligned properly. Okay, that is what is, and the word super means the effect is strong. That is what the word super is used. Okay, am I clear? So, that is something which is very important for you to know. So, I will explain again so that you do not forget. These two books were providing a good example of that. So as you know, for nanocrystalline ferromagnetic material, important thing is that interaction energy among this exchange energy, interaction among the exchange energy, anisotropic energy and dipole energy happens. For very small particles, the exchange forces are dominant due to the strong coupling effect. So therefore, it can lead to all the spin and NMR gains to align, superseding effect of anisotropic energy or demagnetic energy. But there is a critical size. Okay, that is what is shown here. This is what is plotted in the last diagram. I am plotting again a C versus this diagram, and this will be like this. Okay, and you see here, this is the multi-domain particles, and this is the single domain particles. And this is therefore D critical, below which the coercivity increases rapidly, and this is the single domain particle itself, all the spin align, and this is what is D superparamagnetism, below which this situation will happen. Figure 8.6 from Dieter Boller's book. So this is something which is important, and this D critical can be given as 9. Don't try to derive it. This is derived. I am just giving you the value. Okay. So where gamma B is equal to 4 A K1 to the power half, where A is a constant, and this is basically wall energy. A is a constant, energy constant, and it is known as exchange stiffness, and K1 is an anisotropic constant. Okay. Mu anyway is permittivity, and this free space, and MS has saturation magnetization. It is MS, not MB. Okay. So important aspect to know. It basically, what does it tells you? It tells you the effect of magnetocrystalline anisotropy. Magnetocrystalline anisotropy will try to align the spins properly, and thermal energy will try to disturb the spins. Okay, that's what happens. So, if the particle size again said below the critical diameter, the material is single domain, and basically for cobalt this is about 70 nanometers, for iron is 50 nanometers. If the particle again size becomes significantly smaller, that is few nanometers, then critical diameter, then magnetization is likely to become unstable, and then loss of magnetization occurs because of thermal fluctuation. That is what is the D superparamagnetism, what is written here. At this position, that is what will happen. Thermal effects will supersede the the crystalline anisotropy effect. Crystalline anisotropy effect will allow the spins to align in particular directions, okay, or easy magnetized directions. Thermal energy will make them random. So, when these two are balanced out, that is why the superparamagnetism starts, and below this value everything will be completely random, or you have a zero value of coercivity. That is what is known as superparamagnetic behavior. Well, other than that, there are other effects like magnetic properties are also affected by the scale. Okay, what is that? Well, coercivity of a ferromagnetic material is obviously increase or decreases with grain size, and reaches a maximum value within a size range of critical diameter. Okay, coercivity is reaching a maximum value. You can see here that value is at a certain value of D. Okay, D0, correct. So, if the particle size is further decreased, the coercivity decreases rapidly, magnetization becomes unstable, and within this regime hysteresis can be completely gone. You will not see any hysteresis in the superparamagnetism. Okay. Why? Because there is no remnant magnetism. So, why you will see hysteresis loop? You will see a single line like that. So, what you will see is very simple like this. If I plot B versus H in superparamagnetism, you will see like that. They will not see any hysteresis loop because there is no coercivity. So, for the amorphous iron, nickel, cobalt, which having amorphous mostly nanocrystalline, not amorphous, about 10 to 15 grams grain size, practically shows no hysteresis loop. Okay, so technically point of view, if the idea is to fabricate a permanent magnet, coercive force should be as high as possible. So, for these things cannot be used, but they can be used for nice switching operations, because you have no hysteresis loop, so no loss of energy, right? You understand that. So, you like to have a superparamagnetic effect to be utilized in case of switches. In addition to coercivity, magnetization reversible also is strongly affected by the size. Magnetization reversible means if you are changing the magnetic field, the magnetization reversible will happen. The spins will align in the direction of the field. So, if you reverse the field, this is what should happen. So, within a specific range of this diameters, typically greater than the superparamagnetic diameter, but lower than the critical diameter, the exchange interaction energy is sufficiently strong to keep the spins aligned during the reversible process. Above this range of diameters, but still below the critical diameter is the critical, okay, the process of magnetization reversible become very incoherent, involving switching of the small volumes of material within the magnetic nanoparticles or nanograins. The size of magnetic nanoparticles or the grains also has an effect, basically has strong effect on the saturation magnetization. Magnetization basically increases below particle size. Okay, so that's something which is also important. So, nonetheless, what you need to know is very importantly this curve, which is shown here also, the effect of particle size on the coercivity and the remnant magnetisms. This is something which is very important for you to remember. So, by this we have almost done on the magnetic properties of nanomaterials, and there will be some small discussion may require, which I will do in the next class, and upon that I am going to discuss about optical properties of material. That will conclude all the properties for you, because I need to spend some lectures on characterization of the material. So, therefore, I will not wind up all that, I will not take all the lectures on properties, I need to keep some lectures free. So, if you have any questions, we will discuss further. Thank you.